Hello, this video is about computer-aided manufacturing, also known as CAM. So what do we use CAM for? So CAM is used to take a 3D model that you've created in CAD and then generate a toolpath so that a tool such as a CNC mill can then cut that part out of a piece of metal. So in order to download the software you need to make some CAM, you need to go to the Autodesk website. Make sure that you're signed in, as you can see here, and then click Menu. Scroll down to downloads, and then here you can click on free student software. Then when you're here, you're going to want to scroll down to Inventor Cam. Then you can click Get Product. Then you make sure that your settings are right, and you can just click Install, and then the installer will guide you through the rest of the process. Of course, I'm not going to do it now since I already have it installed. After you download the software necessary, you'll need to import the tool library, which will be found in the link in the description of this video. After you've downloaded that, to install it, what you're going to need to do is click on Tool, go to the CAM tab up here, click on Tool Library, then in My Libraries, you're going to want to right click and select New Library. And then you're going to want to rename this library to whatever you want to name it. So for example, I'm going to name this CAD Camp. Next, what we're going to do is right click it and then click on Import Tools from Library. Now you're going to want to look to wherever you downloaded your tool library, and it should be an HSM lib file. Then double click it, and then your tools should be all in here. Then you can just hit OK and you're done. A robot usually has 2 gearboxes, so here I've placed a total of 4 gearbox plates, 2 for each gearbox, and constrained them into a plane and moved them together so that they fit within a 12 by 12 square. After you create your assembly, you need to make a setup. To do that, click the Setup button. Next, you're going to want to set the origin. To do this, click on the Stock Point button, and then make sure you click on the lower left corner, and you want it to be on the top part of it, as shown here. You're going to want to make sure that your x-axis is going horizontally, and the y-axis is going forward and backwards. And you're also going to want to make sure that your z-axis is going up and down. If your origin isn't already in this configuration, then you're going to want to go to where it says orientation and click select X and Y axes, and then you'll have to manually select the X and Y axis to make sure it lines up. Next, we're going to want to go to the Stock tab. Here, we're going to select Fixed Size Box, and then we're going to give this an X and Y of 12 inches by 12 inches. And then we're going to want to give this a height of 1/4 inch, since that's how thick the plates are. We tend to want to drill our holes first. However, if we go back and measure what size holes are here, then you'll see that we have a 0.159 sized hole. That means we'll need to use a 0.159 inch drill bit. So click Tool and go into your tool library, and you're going to want to scroll down until you see a 0.159 size drill. You're going to want to select this, and then you can click on the hole that you want to drill. But instead of clicking on every single hole, you can click on the checkbox which says select same diameter, and that automatically will select every hole of the same diameter. Next, we're going to want to go to the Heights tab, and then select drill tip through bottom. And then we're going to want to set a breakthrough depth of 0.05 inches or 50 thou. We're going to want to do this because we want the drill to drill all the way through the plate, and we'll have sacrificial material at the bottom to prevent the drill from hitting the table at the bottom. This way we get the hole that actually goes all the way through, and it's actually useful. Next, we're going to want to drill the next set of holes, which if we measure, it's 0.196. So next, we're going to select drill, and then we're going to go to tool, and then go to the tool library, and then select a 0.196 drill. Now, this drill, as you can see, is in tool slot number 9. However, the 0.159 inch drill was in tool slot 8. This is so that we can use both drills at once in the same program. This is so that we don't have to use a different setup in order to drill a different size set of holes. Next, we're going to want to do the same thing as we did previously. Select the hole, select same diameter, drill to bottom, have a breakthrough depth of 50 thou, and hit OK. Next, we're going to want to cut the bearing holes. In order to do this, we're going to use a 2D contour. Now, the difference between a 2D contour and a 2D pocket is that a 2D pocket mills out the entire material within a hole. However, a 2D contour only mills the contour of a hole. Now, we're going to be using 2D contour because it saves time because we don't have to mill the entire area in the hole. And using that just leaves a chunk of metal in the center that would otherwise be a waste of time having to mill that. Now we're going to go here, and then we're going to click tool and select a 1/4 inch end mill. This is designed to cut sideways in order to cut the features that we want to do. In this case is the bearing holes. Now we can select each one of the bearing holes. Be sure to click on the bottom edge of the bearing holes, otherwise it will not cut properly. Now if you accidentally click on the top edge, you can hold shift and click it again in order to remove that selection. We can then go to the next tab, and then we're going to want to go to bottom offset and hit negative 50 thou. Now this is for the same reason we had the breakthrough depth, but this is shifting the bottom plane down by 50 thou, which is why it needs to be negative, versus the drill, which was a breakthrough depth of adding 50 thou, versus a breakthrough depth, which was adding 50 thou to how far down it was going. If we go to the next tab, the passes tab, we have to go down and use multiple depths. The reason for this is because a general rule of thumb is you don't want to cut deeper than half of the diameter of your end mill. So since we're using a 1/4 inch end mill, then our maximum depth of cut would be 1/8 inch. So we're going to go to maximum roughing step down and type in 0.125, which is 1/8 of an inch. Next, we're going to want to select stock to leave. Since this is a bearing hole, we're going to want to cut a little bit more than the actual size of the bearing hole. So to do this, we're going to subtract a stock to leave of 0.003 or negative 3 thou. Next, if we go to the last tab, we're going to want to disable the lead in and lead out. This is because it makes the tool curve into and then curve out of the cut as it's before and after it takes the cut. Since the cut is inside the part, having the tool curve in or out would only damage the final product. Therefore, we're going to want to disable that. And that's it for the bearing holes. You can now hit OK and move on to making the motor holes. To do this, we're going to do the same thing, a 2D contour. We're going to use the same tool, a 1/4 inch flat, and the only difference is we're not going to use negative stock to leave. Of course, we're going to select our contours, and then change the bottom offset to negative 50 thou. And then we're going to want to activate multiple depths, and of course set it to 1/8 of an inch. And finally, we're going to want to disable lead in and lead out. Next, we're going to need to machine these little divots in here. In order to do that, we're going to need to use a 2D pocket, because that will allow us to machine the entire area of that divot out. We're going to use the same tool. And then we're going to select the bottom edge of the and we're going to select the bottom of each divot in order to make sure that it machines it, that the program machines it all. Then we're going to want to leave the heights as is. Then we're going to want to disable stock to leave and lead in and lead out. Now when it goes to ramp type, we're going to want to do plunge, because since this is such a small divot, we don't really need any special kind of ramp. Next, we're going to want to mill out the pocketing. Now, we're going to want to select each and every single one of these pockets. It can take a while. Of course, we want to make sure to select the bottom edge of each pocket. Remember, if you accidentally select the top part, you can simply shift click to cancel that selection, and then you can click on the correct part. Now, these pockets actually use a 16th inch radius fillets. And because of that, we're going to need to use an 1/8 inch end mill. Again, go to the tool library and select an 1/8 inch end mill. And make sure that your coolant is on flood. Of course, make sure that your bottom height offset is correct, is at -50 thou. Now, because we're using an 1/8 inch end mill, our multiple depths are going to need to be at 1/16 of an inch per cut. And then, of course, you're going to want to disable lead in and lead out. Finally, we're going to want to do the outer contour of the plate. To do this, we're going to use a 2D contour, and then we're going to select 1/4 inch end mill. From the tool library. Once we have that, we can of course make sure that our coolant is on flood, and then we can select the outer contours of each of the plates. Now, because we're machining the outer contours, we're going to actually want to enable tabs so that the plates don't just fly off once it gets cut out. Now, in order to do this, we're going to want to make sure that the tabs are strong enough. To do this, we're going to make the tabs a bit wide. It's approximately 3/8 of an inch, and then I like to keep the height of my tab at 90 thou. And then play around with the distance until you get tabs that just look about right, and in order to support the plates. So in this case, it looks like 1.2 inches is good. Next, we're going to want to go to the heights and then change the bottom offset to -50 thou. And then we're going to want to make sure that multiple depths is enabled, and we're doing 1/8 of an inch per cut because we are using a 1/4 inch end mill. And finally, we're going to want to disable lead in and lead out. Next, we can actually simulate this. Now, if you click on the setup, and then we can click on the simulate button, and then click the check mark next to the stock button, we can see how the final plate will look like after the mill cuts the plate. As you can see, it starts off by drilling the holes. And we can use the slider at the bottom to speed up or slow down the speed of the simulation. We can even go in reverse. As you can see, it next machines the bearing holes. And then the motor holes. And then the divots. And then as you can see, the 1/8 inch end mill does take quite a bit of time in order to cut the pockets, which is why in real life we would tend to use a 1/4 inch end mill for everything, and in order to save time for milling. So we're just going to speed this up a lot in order to make sure that this finishes. And then finally it does the outer contour, and you can see the tabs where the piece is held, where the final plate is held in place, and that it doesn't just go flying out. Finally, we can skip to the end and look at the finished simulation. As you can see, we can see that the bearing holes are a bit oversized by the fact that the metal is showing there. Now, finally, in order to we need to post-process this into G-code, which the mill can understand. In order to do this, we're going to want to make sure that we select the Haas pre-NGC mill type, because that's the one that we have at Middleton. And your program name and number can be whatever you want it to be. So I tend to have it at 0001, and whatever fits on my flash drive. And the program comment, I'm going to label this CAD Camp Cam, since that's what this is. Now in here, you're going to want to actually make sure that you select preload tool to no, because the mill type we have at Middleton does not have a tool preloader, and we're going to want to make sure that the built-in high feed rate is at maximum 400. Finally, we can click post. And then if I bring the screen up here on my flash drive, we actually have 0001 through 6 filled up. So we're actually going to rename this to 0007 and save. Here you can see the actual G code, what the machine can understand in order to mill this plate. Next, we can make a setup sheet, and and then you can just save that wherever is easiest for you to access. So I'm just going to save that here. And if we pull this up, you can see that it says that the setup sheet is for program 1001, and the job description is setup 2. And the image is not very useful. So what we're actually going to want to do is we want to click on setup so that it shows the yellow bounding box. And then we're going to actually want to go into the setup and then change that program name and number to 0007 and the program comment to CAD Camp. That's a tongue twister. Then we can make sure that the yellow bounding box is highlighted, and then we can actually click, then we can click Tool Isometric to get us this nice view, and then click on the Setup to in order to get that nice bounding box. In this view, we can actually see where the plates are relative to the stock, and we can actually see where the origin is, which is on the bottom left hand corner. Now the setup sheet actually gives you some quite useful information. For example, it shows you what all tools that the program will be using, as well as each type of operation that it's going to perform on the part. After that, provided you have your parts drawing ready to go, you're ready to start milling.